straight for him. All right, so what we'll do, we'll try
them against the wall. This could like 10.
You managed to kill him this time. Yeah. All right, so what we'll do, we'll go through these questions together. We'll sort of summarise the vectors content. You might remember we spent a very long time working through vectors. It's a fat unit. But we're going to summarise, basically, I've broken it up into here's content, here's the number of questions that summarise the content. Chapter 5 is very straightforward, so let's get straight into it. We have 3 points in space, three-dimensional space. We have point A, which is 314, B, which is -201, and C, which is 1, -4, 2. All right, find the vector from A to B. So that's just the coordinates of B, take the coordinates of A, and it's a vector. So we use square brackets to denote the vector. -2 take 3, 0 take 1, and 1 take 4. Okay, there's vector AB. Find vector AC. It's the coordinates of C, take the coordinates of A. 1 take 3, -4 take 1, and 2 take 4. That's 2. Very good. Okay, find -AC plus AB. Alright, so that means we multiply AC by -1 and we're adding it to AB. So it'll be 252 plus -5, -1, -3. We just add the x components, the y components, and the z components together. So -3, 4, and -1. Okay, find 2AB. This is just 2 times vector AB. So -10, -2, -6. Find AB dot AC. So this is the x times the x plus the y times the y. So we have -5 times -2 plus -1 times -5 plus -3 times -2. We get +10, +5, +6. Okay, find the angle between AB and AC. So this is where our notes book's helpful. I can't remember the formula by heart. Something like modulus on top of dot product. So we got the direction just before we did cross product, before we did vector. That important equation. All right. We have cos theta equals A dot B on the modulus of A modulus of B. So that's our formula for the angle between two vectors. Okay, so the angle, we're finding the angle between AB and AC. We've already done the dot product of AB and AC, that's at the top. So what we'll have is we'll have cos theta is equal to 21, there's the dot product of them, on top of the modulus of AB times the modulus of AC. So the modulus of AB will be the square root of 5 squared plus 1 squared plus 3 squared. So that's 26 plus 9 is 35. And then this one, 4, 29, 33. And we'll evaluate theta. So 3 sig figs. Square root of 35 times 33, 0.9047 radians. 0.905 C. See? Okay. So that's question 1. That's a recap of some fairly basic operations with vectors. Any questions about that one? I would expect us to be able to recall that, I reckon. So I reckon you could have done all that by yourself. Okay, let's turn the page and we have a vector proof. Vector proofs are fairly common exam questions, okay? I'm saying over 50% of exams have vector proofs in them. And there's a short exercise in the textbook, but remember we supplemented that in your notes books with about 3 double pages of vector proof questions. So there's lots there to have to practice that. This is a good old exam one. So we have consider triangle OAB, and we have OA is A and OB is B. Point X and Y lie on OA and AB such that OX equals 4XA. Alright, so this is X and this is Y. And they're broken up such that 4 times XA is equal to OX. So 4 lengths of this is equal to this. So it's in a ratio of 4 to 1. Right? 4 parts to 1 part. And the same with this component over here, 4 parts to 1 part. There's 5 parts in total. But XA, 4 times XA is equal to OX. Alright, in terms of A and B, find vector from A to B. Okay, so the vector from A to B is going to be minus A plus B. Alright, so remember we've defined this vector is vector A, this vector is vector B. So when we want to go from A to B, we're going to invert that one, the negative of it. So minus A plus B. That's our answer for part A. That's for A part 1. A part 2 says find vector OX in terms of A and B. Well, the vector from O to X is 4/5 of vector OA, which is 4/5 of A. Okay, use a vector proof to show that XY is parallel to OB. So if these are parallel, then this is going to be some scalar multiple of this one. So what we want to do is find vector XY in terms of A and B. So a couple of ways to do it. We already know what vector AB is. I would be thinking about it like this, like let's find, we want to know vector XY. So I'm going to say, let's find vector AX plus, we're trying to find vector XY. So let's find vector XA, the vector from X to A, plus the vector from A to Y. Alright, we want to know vector from X to Y, so let's find vector XA plus vector AY. Now vector XA, that's just 1/5, okay, it's 1/5 of vector OA. And vector AY is 1/5 of vector AB. Now we've already defined vector OA. Vector OA is just A, so we have 1/5 of A. And vector AB is minus A plus B. And when we collect this, we're left with 1/5 of B. Alright. One-fifth of OB. XY is 1/5 of vector OB because, therefore they're parallel because they're scalar multiples of one another. Okay, is that part okay so far? Very good. Right, do you want to pause a little bit? Okay, part C says, if A cross B equals 4, find the area of triangle OAB. Okay, so the area of a triangle, like if we have a triangle that's composed of vectors A and B, the area is half the modulus of A cross B. So in this circumstance, we're told A cross B is 4 units. So the area of this triangle then is going to be half of 4 units. So triangle AOB, 2 units squared. Okay, so that one's pretty straightforward, triangle OAB. What about triangle XAY? Well, what we have here, if we want to know the area of triangle XAY, it's equal to half, and what we have going on here is we have the modulus of, we have 1/5 of A cross 1/5 of B. All right, so 1 on 5 is a common factor, so what we can do is pull, sorry, it's not a common factor, we're multiplying them together. That gives us 1 on 25, A cross B. We know the value of A cross B is 4, so we're left with, that's 4. This simplifies to 1 on 50. Modulus of 1 on 25 is 1 on 25, so we have 4 on top of 50, or what's that, 2 on top of 25 units squared. Okay, so all we're doing there, when we have modulus, that's a property of modulus, we have modulus of k times some vector A, we can write that as modulus of k times the modulus of vector A. Okay, so we're recognising 1 on 5th of A, we're multiplying the scalars together, that gives us 1 on 25, and then pulling the modulus of 1 on 25 out front. All right, any questions about the vector proof? Okay, so we're going to make sure you practice those. I really encourage you to. They're very common exam questions. All right. So then we got into, we did a chapter 5, and then we got into more of chapter 6. So we did area, lines in 2D, lines, angles between lines, and so forth. Let's get into these ones. So here we have a sailboat moving with a parametric equation, and we've recently done parametric equations, haven't we? So this will be a pretty straightforward recap, hopefully. When is it closest to a buoy located at -5, 2? So let's talk about this line here. What this is the equation of a line in parametric form. What we have is we have the initial point that it goes through plus some parameter multiplied by its direction vector, -3, 1. Now we can plot those points out for t is 0, 1, 2, 3, etc. We can plot those on a Cartesian plane. We can even graph this line pretty straightforward. All right, what we would do, we would go, all right, the initial point is x is 1, y is 4, so it's going to be like up here. And for each value of t, it goes to the left 3 and up 1. So 1, 2, 3, up 1. Okay, 1, 2, 3, up 1. So the sailboat is following that path, isn't it? Although for positive values of t, it's moving in this direction. Okay. But that's the equation of its line. All right. When is it closest to a buoy located at x is -5, y is 2? So that's going to be way over here. So what we're going to do is the shortest distance between a point and a line, and that occurs when they're perpendicular. Now we have a formula for that as well, so we'll flick to that. The shortest distance between a point and a line. It's big lines in 2 dimensions. So that's from exercise 6E. So it's when, now if I'll just define these points, we have, this is vector B. Let's call vector B its direction vector. Okay, and we'll call this is point P. And I'll just voice it the same way that they've got it in the book. This is point R. Now they're going to be closest when PR dot B equals 0. So that's when they're perpendicular, right? PR dot B equals 0, where B is the direction vector. Okay. So, now the point from P to R. Remember, R is the equation of this line here. And so R, the coordinate R depends on the value of T. We don't know the value of T. So if we're going to find the point from P to R, and the coordinates of this are -5 and 2, all right? And the coordinates here, I'm going to list them in coordinate form. The x1 is going to be 1 take 3t, and the y1 is going to be 4 plus t. Okay? Now those coordinates represent any point along this line, and so what we're going to do is we're going to find vector PR. So that's going to be the vector between this point and any coordinate on this line. So let's do that first. Vector PR. So it's going to be the coordinates of R take the coordinates of P. So we'll have, 1 take 3t, take -5. Write it out slowly. The x, so vector from P to R, coordinates of R, 1 take 3t, take -5. There we go. That's the x. And for y, 4 plus t, take 2. All right. So we have 1 plus 5, that'll be 6 take 3t, and 2 plus t. Okay, what this represents is the vector between P and any point along this line. And we want to know, when is this vector perpendicular to this direction vector? So what we're doing is we're going to do PR dot B. So let's write that out here. PR dot B equals 0. So that's going to be 6 take 3t and 2 plus t. Dot, and the direction vector is -3, 1. All right, let's evaluate that. So we'll have -18 plus 9t plus 2 plus t equals 0. Now we've got 10t equals 16, t is 1.6. Now, all we've done there is determine the value of t when that occurs. Now remember, we're asked to find the shortest distance. So we want to know, well, what's the coordinate r? Well, so there's two ways to think about it. The first is go, what's the coordinate of r when t is 1.6? So we can put that into here, find r, find the modulus of PR. But remember, we've already got vector PR with regards to t, so we're just going to plug it back into here. We're plugging t is 1.6 into here to determine the vector PR. So that's going to be 6 take, now 3 lots at 1.6, that's going to be 3.25, 4.8. So 6 take 4.8, and we'll have 2 plus 1.6, 3.6. Now 6 take 4.8 would be 1.2 and 3.6. So that's the vector from P to R. We just want the modulus of that vector. So that's the square root of 1.2 squared plus 3.6 squared. I'll do that. I'll just go straight to 360, you reckon? We've got 3.795. 3.80 to 366. Sorry, it's 3.794, which is 3.79. All right, so is that one okay? So I've sort of dragged that on a bit. Using this formula here, we found vector PR. We did the dot product to make them equal to 0. That gives us the value of t. And then we use t to determine the modulus of the vector PR. Okay.
Is the modulus relevant at all to the question?
Yeah, because doesn't it say find the shortest distance?
No.
Oh, does it say just say when is it closest? Yeah, okay, cool. We didn't need to go on and find the modulus. We just needed to know the value of t. Yeah, good point. So it's when t is 1.6. Okay, how fast is the sailboat travelling? So speed is just the magnitude of the velocity of the velocity vector or our direction vector. So the speed is going to be the square root of, and we look at the the direction vector, 3 squared plus 1 squared, we have root 10. Now let's think about, we defined any units, we've got distances are in meters and time is in seconds. So square root of 10 meters per second, so just over 3 meters a second. That's how fast the sailboat is traveling. All right, we have the equator is given by y equals minus x take away 10. When does the sailboat cross the equator and what angle does it make with it? Okay, now minus x take away 10, that's going to be, like if we think it has a y-intercept of minus 10 and it has a slope of minus 1, so a slope of minus 1 is going to look like this. I might zoom out a little bit and draw another Cartesian plane. So let's say we've got minus 10 here, and for our sailboat we had 1, 4, and a slope of a third, so it's like this, very shallow. Okay, and then this one, slope of minus 1, like that or something. Okay, so we've got, here's where the sailboat is crossing the equator line, and find the angle between them. So, what we'll do, let's determine when it occurs first. So we want to know, when does this line meet this line? And the line is minus x plus minus x take 10, minus x take 10. Okay, so what we're going to do here is we're going to think about that line. Okay, this is in y-intercept form, and let's convert this to parametric form. Okay, we're going to provide it with some parameter. So it's quite easy to do for us. We have an initial coordinate. We've got when x is 0. We know the y value is minus 10. So we have a coordinate, and then we have some parameter. Let's use lambda multiplied by its direction vector. And so its direction vector is it's got a slope of minus 1, so that means it's going across 1, down 1, across 1, down 1. So we can just go like this. Okay, so that's one way we can express the line in parametric form. So now one thing we can do is like equate the lines. That's one way of going about it. I reckon an easier way though, is going to be just to substitute this line into this one and find the value of t such that it satisfies it. Okay, so if we have y equals minus x take away 10, well we can sub the x value from here into here and the y value from here into here and solve. So I think that's going to be the best way to do it, isn't it? So let's do that. We've got 4 plus t is the y value, and it's equal to the negative x value, which is 1 take 3t, and then take away 10. And we can now just solve this for t. Okay, that's going to be when this line meets this line. So yeah, sorry to take a little bit of a tangent there, just showing you how we can move from Cartesian form to parametric form. Alright, so let's solve this. First we'll expand that bracket, minus 1 plus 3t, and put all the numbers on the left side. So we've got here minus 10, so that takes us to minus 11. We'll move it over this side, we'll get plus 11, that takes us to 15 over here. And on this side, we'll have 2 lots of t, and so we get t is 7.5. So when time is 7.5, after 7.5 seconds, the sailboat crosses the equator. And then to find that angle between them, all we're doing is finding an angle between the direction vectors. So the direction vectors are minus 3, 1, and 1, minus 1. And remember, so we won't go through this, well, let's go through it really quickly. So we have the angle between two vectors is a dot b on modulus of a modulus of b. So in this circumstance, minus 3, take 1, yep, on top of the square root of 10, square root of 2b. Alright, we'll evaluate theta. 2.67 radians, so that's going to be this one. Okay. Alright, so that's question 3. Let's jump to question 4. Consider the lines in space. Find the relationship between these lines. Okay, so this is going to be a good recap. Here we have lines in 3-dimensional space. And so let's just have a recap of what are the possibilities for the lines. They could be the same line. Okay, we call that coincident. They could be parallel, in which case they have the same direction but will never intersect. Okay, parallel. They could be skew, in which case they never meet and they're not parallel. They're not going in the same direction. It could be skew lines. And the last one is that they could intersect at one common point. Okay, cross one another. So, what we're doing is we're finding out what's the relationship between them. So what we're going to do, let's present it as a matrix and solve through. All right, what we'll try to do, we're going to try and find a common solution and check if it works. So the lines that we've got line 1 passes through the coordinate 3, 0, 2 and has direction vector 4, 7, 3. And we've got line 2 passes through 4, 6, 0 and has direction vector -3, minus.
No, that's line 2 passes through 2 points.
Oh, yeah, cool. Okay, it passes through 2 coordinates. Yeah, good pickup. So we need to find the direction vector. Good. Yeah, so that's very easy to misread that. 4, 6, 0 and -3, -1, +2. Okay, so let's find the direction vector of this line. So we'll do -3 take 4, will be -7, -1 take 6, and 2 take 0. Pick up, Joe. So that means line 2 in parametric form is, we go through 4, 6, 0, plus, we have to use a different parameter, some parameter lambda, -7, -7, 2. Okay, there we go. Okay, now the way we're going to solve this is we'll follow the steps that's listed in our notes book. Now we can see, firstly we can see that they're not parallel because the direction vectors are not scalar multiples of one another. So the relationship between the lines is not parallel. And this also means they're not coincident, because if they're coincident, they're the same line, which means although they might have a different point, they're going to have, again, scalar multiple of direction vectors. So they're not coincident. This means they're either skew or they intersect. So what we're going to do is we're going to try and solve the point of intersection. Now we'll get a value, and then we need to determine if that value is consistent with all of the equations. So let's start with x. For the x value of line 1, we have 3 plus 4t, and we're going to set, I'll just write that here, x value. So we have 3 plus 4t for line 1, and for line 2, it's going to be 4 take 7 lambda. Okay, that's the x value. Let's do the y value, we'll equate the y value as well. So we'll have 0 and 7t for line 1, and we'll have 6 and -7 lambda for the y value. Okay, we've got two simultaneous equations. What we're going to do is we're going to make it ax plus by equals c. So I'm going to put the lambdas and t's on the left-hand side. So we'll have here 7 lambda plus 4t equals 1. That's what this equation rearranges to. We'll solve this one. We'll have 7 lambda plus 7t equals 6. And I'm just going to solve them in my calculator simultaneously. So it's a good refresher because this is a skill you do use in methods as well. So we menu, equation, simultaneous, and there's two unknowns, and all we're doing is inputting 7, 4, 1 for the first equation, and 7, 7, 6 for the second equation. And I've got minus 17 on 21 for lambda. And I've got 5 on 3 for t. Okay, so that's telling us that's where they intersect. Now the way we check if it's consistent, all right, is we're going to put t is 5 on 3 into line 1 to determine the z value. And we're going to put lambda is minus 17 on 21 into line 2 to determine the z value, and we're going to see if they have the same z value. So when t is 5 on 3, line 1 z value, I'm just going to evaluate the z value because we don't need the, we're going to have 2 plus 5 on 3 times 3, so that's just going to be 7. And when lambda is minus 17 on 21, what a bell today. We have line 2 z value is minus 17 on 21 times 2, which is what, minus 34 on 21. Okay, these are not the same, which means there is not a common solution. There's no common solution, which means they don't intersect, the lines are skewed. All right, good. We'll stop there for recess, and when we come back, we'll do question 5 and 6 overleaf. Everyone okay so far? Any questions? Okay, so find the equation of a plane composed of line 1 and line 2. Oh, dang, I rubbed out the equation of line 2, but you guys will have it. So line 1 is 302 plus this parameter, 473. And line 2, we said goes through this coordinate. I remember it was 7, minus 7, minus 7, 2.
Yep.
Oh,
Okay. Cool.
all right, so if we want to find the equation of a plane that's composed of 2 lines, now these are skewed lines, so that won't work. Let's just perform the maths for it anyway. So what we have is we need to find a vector that is the cross product of both direction vectors. So if we're going to do the cross product ijk, so we're going to do the cross product of this vector and this one here, both direction vectors. So what we're going to do here, we're going to perform the mathematics for a plane that doesn't technically, like the maths is going to work out, although because they're skewed lines, they don't share a common plane. Okay, so we've got 4, 7, 3, and we've got minus 7, 2. Okay, so we're doing the cross product. So I'll refresh you how to do that on your calculator and how to do it manually. Most of the time, they take about the same time to do it both ways. So calculators sort of, you'll probably make less mistakes. So what do? We cover up I and we do AD, take BC. So we've got 14, take minus 21. And then we have I minus J. And we cover up J and we go, yep, AD, 8, take minus 21. And then plus K, and we do minus 40, minus 28, take minus 40. 77. And that's plus, it's 49, take 28, 21.
Should it not be 35?
This one. Good. I might just check it on my. So in program, A cross B. So we have 4, 7, 3, minus 7, minus 7, 2. 35, minus 29, 21. Good. Okay, so that's the equation of the normal. So that means that we have 35x, take 29y, plus 21z equals d. And the way we find the value of d is we substitute in any coordinate that lies on the plane. We know both of these coordinates lie on the plane, so let's substitute this one in, 3, 0, 2. So we have 35 times 3, 29 times 0, and 21 times 2. And evaluate that, so what's that, 1,705 plus 42, and that's 147. So the equation of the plane then, 35x, take a 29y plus 21z equals 147. That is the equation of the plane.
Isn't it? 35 times 3 is 115.
70.
Oh wait, no, it's 105, yeah.
Yep, good.
What was it? I swear there was something that we did better than
I swear before it was 100.
I swear.
That's just joking. Okay, part B. Find the shortest distance from the point 304 to the plane. Alright, so the shortest distance between two lines, angles in space, intersecting planes. We have a formula for this in
This doesn't.
angles between two planes. The shortest distance from, so it's on page 48 of our notebook, so we'll write the formula up here. D equals the modulus of ax1 plus by1 plus cz1 plus d on top of the square root of a squared plus b squared plus c squared. Alright. Where a, b, c, these are our values of a, b and c. D is going to be minus 147 when we bring it over, and x1, y1, z1 are the coordinates of the point that we want to find the distance from. So we'll just write it out as a big crunch. So we have the modulus of, and we've got 35 times the x coordinate of the point. Now the point we're interested in is 304. So we have 35 times 3, and then plus the y. Take 29 times 0, plus 21 times z value is 4, and then take 147, modulus of that, on top of, at the bottom, 35 squared, 29 squared, 21 squared. And so it's just a matter of evaluating that. So we got 189, take 147, we've got 42 at the top, on top of, and at the bottom we've got something big. $50.0. 42 on 50.1. 0.838. Units. So the point is very close to the point. Alright, so just processing the formula there. So what did we do? We found the equation of a plane, and then we found the shortest distance between that plane, this plane, and the point 302. Alright, so everyone remember that? So for a plane, it's just the normal vector between the two, and then we sub in a coordinate. Very good. Okay, we've got one more question over leaf. And we have a set of equations. All right, so we're going to express it first in row echelon form. So we have x take 3y, take 2z equals minus 9. So I'm just going to go straight away to row echelon form. We have 2 minus 5 positive 1. And that equals 3. And we have minus 3, 6, and 2, and 8. Okay. Now, we don't have to identify any parallelism at this stage. We're just going to start to reduce it in order to discover what situation it maintains. So I'll just point to you in the notes book. Remember when we have planes in space, all right, there's 8 different possibilities. Okay, so we've got 3 planes. Here's the equation of plane 1, plane 2, plane 3. And we're talking about how can they possibly be arranged. So it could be they're all the same plane, could be 2 of them are the same plane and 1 intersects. We've got 8 possibilities there. Let's crack through it and find out what's the solution here. And the way we do that is we reduce the system down. So we're looking to first put a 0 here, then we're looking to put a 0 here, then we'll use those 2 equations to put a 0 here. Okay, that's what we're going to try and do. So if I want to put a 0 there, first step, what I'm going to do is I'm going to replace row 3 with 3 lots of row 1 plus row 3. So row 1 and 2 stay the same. Now 3 plus minus 3, that's going to be 0. We have minus 9 plus 6 will be minus 3. And we'll have minus 6 plus 2 will be minus 4. And minus 27 plus 8 will be minus 19. Okay. Alright, next we'll replace row 2 with 2 lots of row 1, take away row 2. Take 2, 0, and we have minus 6 plus 5, minus 1, and then we'll have minus 4, take 1, minus 5, minus 18, take 3, minus 21, okay. And then we want a 0 here, so we will do, we're replacing row 3 with 3 lots of row 2, take away row 3. Take minus 3, that becomes 0. Then we have minus 15, take away minus 4, so that's going to be minus 11. And then minus 63 plus 19. Minus 63 plus 19, 44. Okay, so what we've got here is a single point of intersection. All right, so we can look at, again, our notes book here, and if we have this form, it's circumstance 6, where all 3 meet at 1 point. So just that's what the row echelon form matches. So let's solve it. What we have is we have minus 11 lots of z equals minus 44. So the z value is positive 4. All right, then I have minus 1 lot of y, take 5 lots of the z value, equals minus 21. So minus 20, so we get y is positive 1. And then For x, we have x, take 3 lots of y, take 2 lots of z, is minus 9, so that's here minus 8, that takes us to minus 11, so x is positive 2. So we've got a solution where the 2 planes meet, 3 planes meet, sorry, 2, 1 and 4. That's the coordinate where all 3 planes intersect with one another. Okay, so there we go. That's it for vectors. Any questions?
Yeah, there was a bit earlier.